So another useful law in working with gases is Dalton's law of partial pressures. Dalton's law of partial pressures is very simple. It simply says that if you have a mixture of gases, the total pressure of that mixture is the sum of the pressures of each gas if it were by itself. We call those partial pressures. Okay? So P total equals P1 plus P2 plus P3, etc., however many gases you have. And if we use the ideal gas law, we have P total is equal to the total number of moles, because moles and pressure are related, times RT over V. So here's a couple of, an example. We have some hydrogen gas, 2.9 atmospheres of pressure, or 0.60 moles. And we have in another container some helium at 7.2 atmospheres. There's 1.50 moles of that. If we put them together, the total pressure will be 10.1 atmospheres. We add the two, 2.9 plus 7.2. And the total of moles will be 2.10 moles. We just add the two numbers of moles. So it's very simple. You're just adding. Okay? So here's an example. We're going to put 46 liters of helium and 12 liters of oxygen, which are currently at 25 degrees Celsius and 1 atmosphere, so room temperature and atmospheric pressure at sea level. But we're going to pump those into a 5-liter tank. You might see this when you go scuba diving. Deep sea diving, in order to avoid getting the bends, which is when nitrogen bubbles build up in the bloodstream, it can be deadly. They mix, instead of oxygen and nitrogen, which is what you breathe in the air, they mix oxygen with helium. Helium doesn't form bubbles as easily because of its very low molar mass and low density. So if you ever do go deep sea diving, your tank will contain a mixture of helium and oxygen instead of nitrogen and oxygen. You talk funny, but you don't die, so there's that. So we've got 46 liters, 12 liters of oxygen. We're going to put them all into a 5-liter tank. Obviously, the pressure is going to be very high because we're squashing these 58 liters of gas into a 5-liter space. And we're going to calculate the partial pressure of each gas and the total pressure in the tank. Okay, so let's figure out what we need to do. First things we're going to do is find the number of moles of each gas. So moles, according to the ideal gas law, N is equal to PV over RT. Finding the moles of helium, we have 1 atmosphere, 46 liters, R is always R, and temperature in kelvins, 298. That's 1.9 moles. Number of moles of oxygen, do the same process, we get 0.49 moles. Okay, so that's how much we're starting with. That's how many moles of gas we're beginning with before we put them in the tank. Okay, so now we want to find the new pressure of each gas in our new volume. Okay, so pressure is nRT over V. We just calculated N. We just calculated the number of moles of each gas. R is still R. T hasn't changed, but now we've squashed the volume down to 5 liters. And so our oxygen is at 9.3 atmospheres, and our helium is at 2.4 atmospheres. So again, Dalton's law of partial pressures, we add the two together, we get 11.7 atmospheres in our tank. You better have a strong tank to hold gas at a pressure of 11.7 atmospheres, because that's pretty high pressure. The important thing about partial pressure is it doesn't matter what gases we use, just how many particles or the number of moles of the gas that we have. So if you have ideal gases, the size of the gas molecule is not important. We assume that there are no forces between the molecules because it's an ideal gas, so none of this comes into play. Okay? If the gas was a real gas, and there were, for example, interactions between molecules, if the molecules were polar, for example, or if the particles were very large compared to very small, those would change a little bit. Okay? So usually we use the ideal gases to do some of this calculation. Now another thing we can look at is something called mole fraction, which is a ratio of number of moles of a component of the mixture to the total number of moles in a mixture. It's just fraction, a small piece over the total. Okay, so we use the capital letter X, a sort of script X, and it's just going to be the number of moles of that substance divided by the total number of moles. If we use our ideal gas law, okay, we'll see that there's a relationship between the total number of moles and the total pressure. So total N is equal to P total V over RT, or N1, the number of moles of component 1, is equal to the pressure of 1 times V over RT. We just sort of can replace some of these things here, and we see that the mole fraction is equivalent to either the moles of one substance over the total number of moles, or you could also look at mole fraction as equal to the pressure of one of the substances over the total pressure, because moles and pressure are related. When we want to work with gases, sometimes we have to make them. And if you just make a gas in the room, in a lab, it's going to diffuse to take up as much space as you give it. So a lot of times we'll create gases through a chemical reaction, and we'll collect the gas by bubbling through water. It's called water displacement. Okay? Now the problem with water displacement, it's a nice easy way of capturing a gas, but the problem with it is that when you do that, you'll always have a mixture of gas, because water evaporates to fill up a space too. And so as you're collecting this gas, whatever it might be, you're also collecting some water vapor. And since water vapor is a gas, it contributes to the pressure. Now, the pressure of water vapor over the liquid changes depending on the temperature, and it'll always be given to you in a problem. Okay, so this would be an example of what a setup might look like. Okay, we'd have a reaction of zinc and hydrochloric acid, and as a matter of fact, you're going to do something similar to this in one of our labs, where you're going to collect some gas through water displacement. The gas is traveling through the tube underneath the surface of the water in the large container, and it's bubbling up into the jar, the upside down jar, and as it bubbles up, it pushes the water out the bottom. So the gas takes the place of, displaces the water in the jar. Well, the fact is, you're not only getting the hydrogen gas, you're also getting some water vapor up there, and the total pressure in that container now is the sum of both of those. Often we only want to know about the gas that we're creating. We don't want water, so we'll have to subtract it out. And that's why you'll need the amount of pressure that water is going to be contributing, which you can either look up or, like I said, it'll be given to you. Okay, so the total pressure inside the space above the water in that jar, in that upside down jar, is a combination of the pressure of the hydrogen gas that we're creating with this reaction and the pressure of water vapor. Alright, so here's an example. I want you to see if you can try this one. Pause the video and give it a shot. Ready? Alright, so let's take a look at what we've got. A lot of information. Let's see if we can figure out what needs to be done here. Okay, so here's the setup that we would use to actually collect the oxygen gas. You can put some potassium chlorate into a test tube and throw a Bunsen burner under there, and it'll decompose. We use a little manganese oxide as a catalyst to help it go. It'll decompose into potassium chloride, and it'll produce the oxygen, which will travel through the tube, and we'll collect it through water displacement. Okay, so the first thing we're going to do is find the partial pressure of oxygen in this situation. So the total pressure is the pressure of gas plus the pressure of water. Okay, and so 754 torr minus 21 torr, which is the vapor pressure of water under these conditions, is 733 torr. So that's the partial pressure of oxygen. We can then find the number of moles of oxygen that we've produced based on that pressure. Moles is PV over RT. The pressure we just calculated, but we're going to convert it to ATM, atmospheres, because we're using an R value that contains the units atmospheres. We've got 0.650 liters, that's our 650 milliliters, and then we've got R, and we have our our temperature is 295 kelvins. And so, according to this calculation, we've got 2.59 times 10 to the minus 2 moles of oxygen that were produced. Now, using stoichiometry, if we know how many moles of oxygen was produced and we have the balanced equation, we can then figure out how many moles of KClO3 were needed. And you don't have to stop at moles. You can go all the way to grams if you want. Just use the molar mass as another conversion factor. Okay, so you should have 2.12 grams of KClO3 needed in order for this experiment to go. So, taking a break from the calculations for a minute, we want to understand the concept of why all of these things work. What's going on with gases? And the broad topic that governs this is called the kinetic molecular theory. Okay? Kinetic molecular theory is a model, which means we approximate gas behavior based on some modeling some examples or some real-world examples or things that we can understand. Okay, some assumptions have to be made. The volume of particles, gas particles, is assumed to be 0. So it doesn't matter which gas you use. The particle size is irrelevant. Okay, the particles have to be constantly moving, and they don't exert forces on each other. In other words, they don't attract or repel each other. No intermolecular forces. It just makes the theory work a little better. Okay. We also understand that kinetic energy is proportional to Kelvin temperature. That's more or less what Kelvin temperature measures, average kinetic energy. Okay? So Boyle's law, pressure and volume. Okay? We're not going to change the temperature, but if we decrease the volume, it causes the particles to become more crowded, and therefore they hit the wall more often. The more collisions you have, the greater the pressure. So this is how kinetic molecular theory works. We just described what's going to happen in terms of the number of collisions. For Gay-Lussac's law, which relates pressure and temperature, keeping the volume constant. If you increase the temperature, you speed the particles up. If they're going faster, they're going to hit each other and they're going to hit the walls more frequently. More collisions equals greater pressure. Okay? Charles' law measures volume and temperature. We need to keep the pressure constant. The way you can keep the pressure constant is by allowing the volume to change. If you allow the volume to change, pressure stays the same. So if we increase the temperature and we allow the volume to change, the volume will increase because these particles will hit the wall more often because they're speeding up. But since one of those walls, the top, moves, it'll move. It'll get bigger. And finally, Avogadro's law, volume and number of moles. If you increase the number of particles, you get more collisions, and if you allow the volume to increase so that pressure can stay constant, then the volume will get bigger. They'll try to take up more space if they're moving faster. That's what kinetic molecular theory is all about.